And it was at that level that you would have to monitor the motion of these mirrors at 10 million times smaller than the atoms in the mirrors. And I thought to myself, that's crazy. And so in this book, which was published in 1973, we went to press just after Ray Weiss wrote his seminal paper. I had not yet really studied that paper fully, but I just knew that this was crazy. And so it describes in a few words Ray's idea in here. And then it says, I think there's an exercise where it says, show why this is not very promising. Just a mild, gentle.
So why would anyone try to listen to the universe by tracking motion so minute that they blur beneath the restless dance of atoms themselves? At first glance, the idea violates common sense. You want to study monstrous cosmic collisions, black holes smashing together with more power than all the stars in the observable universe, and the instrument you build cares about displacements far smaller than the nucleus of an atom. There's a cognitive whiplash in that. We expect big events to leave big footprints. Gravity refuses that expectation. It stretches and squeezes space by a fractional amount, a strain. Across the width of a galaxy, the same strain is epic. Across a few kilometers on Earth, it's subtle enough to be mistaken for silence. But silence to us isn't silence to light. If you let light serve as your ruler and your clock, you can watch the universe whisper in its ticks. That is the first friction. When space itself changes, what does it even mean to measure length? If every ruler stretches, everything should look the same. The escape hatch is geometry and timing. A passing gravitational wave doesn't scale all directions equally. It trades length between perpendicular axes ever so slightly. In an interferometer, beams travel down two long arms at right angles, reflect off heavy mirrors, and recombine. The light waves carry phase, tiny records of travel time. If the wave front in one arm arrives a hair sooner than in the other, the interference shifts. You don't need a ruler that resists cosmic stretching. You need a clock that compares two paths differently affected by the wave. The measurement becomes a story told by the light itself. That grants a foothold. But a foothold on a mountain is not a summit. The climb is everything that conspires to drown that tiny phase shift. Noise doesn't merely surround such an experiment, it occupies it. The ground rumbles with distant storms. Passing trucks nudge the earth. The building breathes. Within the mirror, thermal jostling rattles the atoms. Even the photons you use to measure arrive in a fundamentally grainy way, a quantum snow that makes the beam's brightness flicker. The naive fix would be to pour in more light. Brightness reduces the randomness of counting photons until the pendulum swings the other way. Pummeling the mirror with more photons means more random kicks from their collective momentum. You trade one kind of quantum fuzz for another. There's a limit where position knowledge and disturbance reach a compromise, the standard quantum limit. And here's an unexpected turn. You beat it not by brute force, but by sculpting the uncertainty itself. Inject light whose vacuum fluctuations have been squeezed. Less noise in the variable that matters for the readout, more noise shunted into the variable that does not. You don't eliminate uncertainty. You redirect it, like a sailor trimming a sail to cheat the wind. So you tame quantum prickliness with quantum craft. But the Earth is still loud. The solution is audacious. Make massive mirrors behave as if they float in silence. Suspend each mirror on a chain of pendulums, each stage filtering vibration from the stage above. Let the entire apparatus ride on active platforms that sense and cancel ground motion. Keep the light traveling through ultra-high vacuum, 4-kilometer-long steel beam tubes where molecules are vanishingly scarce. Then fold the light path with optical cavities so the beams bounce back and forth hundreds of times, effectively lengthening the arms. Use mirrors that weigh as much as a person to dampen the impact of photon pressure. Polish them so the surfaces deviate from perfection by less than the width of a bacterium across an expanse of glass. Watch the tide from the moon stretch the land beneath the facility by tens of micrometers, and quietly nudge the optics to keep the interferometer locked to a dark fringe. It's a cathedral to stillness erected on a planet that never stops moving. Even then, the instrument doesn't chase motion. It listens for a pattern. A pattern of frequencies sweeps in time, the telltale chirp of two black holes spiraling together, or the fading ring of a single remnant settling into a final state. And when that pattern appears, it isn't just a detection, it's a dossier. From it, you can extract the masses of the objects, their spins, the distance to their dance floor, and whether general relativity is playing by its own rules in the strongest gravitational fields nature offers. When two neutron stars collide, the gravitational wave signal encodes the stiffness of nuclear matter, hinting at how quarks huddle under unimaginable pressure. The moment their collision lights up the cosmos with a kilonova, telescopes catch the radioactive glow of freshly forged heavy elements. The gold in your ring, and a substantial share of the universe's heaviest nuclei, likely trace their origins to rapid neutron capture in events like these, with neutron-star mergers now confirmed contributors alongside rare stellar explosions. When we caught one of those events, the space-time ripple and the flash of light arrived within 2 seconds of each other after traveling about 130 million light-years, a joint affirmation that gravity and light share essentially the same cosmic speed to within a few parts in a quadrillion. The new sense we built doesn't replace sight. It adds a new verb to our repertoire, to listen. And, with a sense attuned to curves and geometry, rather than charges and fields, we can explore regions that are perfectly dark to every telescope ever made. There's an ethical dimension to all this precision. It reframes skepticism. Real skepticism is not the reflexive dismissal born of discomfort with scale. It's the demand for testable predictions, reproducible methods, and a readiness to be wrong with grace. A century ago, Einstein wrote equations that allowed waves of space-time, and for much of the 20th century, their detection seemed beyond reach. Decades later, the gulf between possibility and practicality looked vast enough to swallow careers. It takes a particular audacity to say that the universe has written instructions in light and noise and motion. We will learn its alphabet. The techniques born of that audacity, quantum control, vibration isolation, precision metrology, spill far beyond gravitational waves. They refine the clocks that keep GPS and deep space tracking in step, stabilize the lasers and frequency combs that calibrate the spectrographs used to find and study exoplanets, and push matter to the brink where classical intuition breaks. The pursuit of something that sounds too small to matter ends up mattering everywhere. And that brings us back to the first question. It's not that we relish measuring absurdly small displacements for their own sake. It's that the universe has chosen a language where the dramas of gravity broadcast in strains rather than in amplitudes, where the loudest crashes translate into the faintest geometrical murmurs at our scale. So why attempt to hear them? Because the thinness of the signal is not an obstacle. It is the price of admission to a realm of knowledge otherwise sealed. When we commit to that price, by letting light be our ruler and clock, by turning quantum noise from adversary to ally, by quieting a world that never quiets, we gain access to phenomena no other method can reveal. We do it because reality doesn't bend to our intuitions. Our tools and our understanding must bend to it. And when they do, those vanishingly small motions become the most eloquent voices in modern science, telling us who we are in a universe that is deeper, stranger, and more generous than our common sense ever allowed. Like if this was interesting, and hit the subscribe for more.